Okay, we'll resume the session. For the second part, we'll be briefly talking about some properties and statistics and probability, like independence and some of the concepts you'll see frequently, which is not that. I mean, it's hard to prove them, but it's not that important until you just need to know like what a theorem basically means. So I'm just talk about like the theorems in case you don't know them, like the large numbers and central limit theorem. And then after talking about it, we'll just talk a little bit about what we do in statistics, because we do a lot of inferences using the probability sense. So after that, we'll end the session quickly, okay? And when the session ends, we'll have some short Q&A session, so you can ask me anything related to the session, related to the math camp, or maybe something other than math camp. It's all fine, okay? And then we'll stop our journey of math camp. Okay. I just wanted to point out a very important property here, which is called independence, which you would have heard a lot already if you have taken some statistics related courses, which is basically we want to think about the cases where when two events are independent. For example, a very nice example is that when you throw when you have a coin and you have a dice, for example, you throw a coin and throw the coin and throw the dice at the same time, and it will give you results. And you remember that the coin toss, the probability is half, right, for head or tail. And for getting the dice is going to be 1/6, right? Because it's going to be 6 possibilities. And you can kind of see whether two events are independent in the sense that whether one event happens or the other event happens is not affected by the other's result. Like, for example, the part of you, just because you throw your coin, is not going to affect the probability of the output you're going to get in the dice, right? So that means like two objects, two events are going to be independent, and that's where the concept of independence comes out. But we want to write it in a bit more rigorous fashion, so this is what we do. So basically what we say is that we say that like two events, they're independent if if A and B is basically same as multiplying PA and PB. So what does that mean? So basically, the left-hand side you can see is basically you're intersecting A and B. So what this is saying is that the probability you're getting from intersecting A and B is same as just multiplying it by each probability. So for example, remember the dice and coin example. So we have a coin and a dice. So coin, you have a head or tail, and dice is not square. Dice. You have a dice, from 1 to 6. So, for example, think about like the probability of A being like you getting head, and B is like you getting number 1, okay, on the dice. And probability of P and PA intersection B is basically saying the probability of you getting a head and number 1, which would be out of all 6. So it should be 1 out of 12. But this is basically same as you doing this, which is you're just doing it separately, right? So this is your probability of getting a head and probability of you getting 1, right? So what does this mean is that if you multiply it, it's the same as just getting an intersection, which is defined as events being independent. And events being independent is just like a special case. You can make it more general by making about random variables becoming independent. There is actually more rigorous way to say what it means for random variable to be independent, but I'm just going to write a bit more less rough definition, which is this. So basically the same. So basically we thought about events only, but events are basically like defined by random variables and the probability, right? So basically you just write it as x and y. For example, when we say two random variables are independent, in this case random variables are x and y. So this is like analogously between A and B. So basically probability of x being less than x, y being less than y is going to be the same as just multiplying them separately, right? So basically we say that two random variables are going to be independent if this holds for all x and y. Okay? So any sort of event, what happens at the x part is not going to be affecting the probability for y, and vice versa. Okay, so that's why it works. And note that this actually holds for n number of events. So I just write it for like 2 cases, but what we are actually doing is that, for example, if we have the case where events are like, there are n number of events from an to a1 to an, what this kind of saying is actually for this to hold, we have to have cases like where you do intersection of all n, and this is going to be same as doing multiplying all the probability of ANs separately, okay? This is actually a bit more of a rigorous definition of an independence overall. It's a more general independence. And the reason I point this out is because it's always important to like kind of distinguish this from the pairwise independence. So what is pairwise independence? So instead of writing this, like this kind of writing the probability separately holds for all sort of n, we can say that maybe this just holds for like 2 elements. Like instead of saying this, maybe you might be tempted to say, maybe we might say this independence if PAI and PAJ can be written separately for all different ing, right? You say that, but actually this definition is not the definition of independence. It's a little bit more lesser condition, which is called pairwise independence. So basically, we're saying like for any sort of collection of A1 to AN, we can assume that it's pairwise independent for just 2 elements. So we just take out 2 elements, and they're going to be independent. But that does not mean that the whole collection of these events are independent, mutually independent. Okay. So, for example, relation between pairwise independent would be like so if it's independent, you can assume that it's going to be pairwise independent. But if it's pairwise independent, you cannot say it's independent, okay? So in a way, independence is like a stronger condition in this case, okay? So you cannot say it's going to go both ways, okay? Just remember this. Sometimes you can get confused by this concept, all right? And it does pop out numerous times. All right. And just reason we kind of use this independent concept, like one of the most frequent places we use it is like when we're doing expectation. So independence concept kind of goes along with the independence of expectation. That is, if you assume that the random variables x1 to xn are all independent, and if they're all defined very well, you can see like in the notation A and B, you can see some weird symbol to go like the random variables are all positive, or maybe the expectation is smaller than infinity. What they kind of mean is basically like the expectations are well defined. So there's not like cases where the expectation is infinite, okay? So in this case, if the random variables are all independent, then we can write the expectation, like in the product of expectation separately. So similar to independent concept, if xi's are independent, you can multiply them inside the expectation, but the value of it is the same as just getting expectation and then multiplying separately. Okay? So it's very easy if you're trying to find a situation where you have to like case where you have expectation of multiplying many independent variables, and if the random variables happen to be independent, you can assume that their multiplication is just like their expectation and just multiplying them all. Right? So basically, independent allows us to separately take expectation. Although there's something more than what independent does, but we won't talk too much about it. But basically, those are the ways we use independence, okay? And also some concept you might need to know later on when you're studying econometrics is that uncorrelatedness, which is also similar to the kind of like a relation between independence and pairwise independence, but in kind of expectation form, okay? So it's kind of different. We don't say it's a similar, so when we say something is independent, like the random variables, we can say that it is also uncorrelated. But uncorrelated doesn't mean that the random variables are going to be independent. So you can see in the definition here. So we have two random variables with ex squared and ey squared is not infinite. Can you kind of guess why we're defining the second moments of x and y to be infinite? 혹시 이거 왜 그 second moment를 finite하게 잡는지 아시겠어요? 그쵸. 그러니까, okay. The reason we are making them finite is because you later see that this EXI, well, I mean, you're not going to see it, but later if you study like statistics, you can actually write this as some sort of like a, I'm not sure if this is the exactly right formula, but by like Cauchy or inequality, you can kind of write this later on as some sort of like this sort of, we bound the EXY by the second moment. And the reason we're kind of making these finite is to make sure this is finite. Okay? Otherwise, there's possibility that EXY could be infinite. Then we wouldn't want that sort of thing to happen. It's kind of related to the variance too. So we're making sure that EXY is defined as well. Otherwise, it's not going to define very well. Okay? And you'll see like these sort of questions always pops up. Like when I did talk about this already. For example, like all these like sort of regulation conditions are sometimes very important for certain conditions to hold. Like remember like talking about Fubini theorem? Remember we talked about like iteration of we talked about the law of the expectation, and you'll later realize it if you read it, if you study this in some econometric courses, when you see this, proving this, they'll have an assumption here that says like, we assume this, okay, to solve this. And the reason this is here is because in order to, if you don't have this defined, you cannot use the Fubini theorem that I mentioned before, right? Because remember, expectation is basically like integration, okay? So making this means basically the integration exists, it's finite. So without this, this cannot hold. So in statistics, a lot of concepts like regularity conditions that you have to remember, because without these, what you think is going to work is not going to work. So although in most cases, it works very well. So a lot of the ways we do it most of the time is like do something like we assume some forced moments like finite or something like this. Because this is usually like strong enough condition to ensure that most of your conditions hold. So you'll see some sort of these like regulatory conditions. It kind of mean like everything you think is going to work out well does work out well. It's kind of like a stronger condition. Okay, although you don't need this always. Just to tell you. So basically, if we have a case where EXY is EXEY, so basically there's just two elements, and we have the case where they're just divided again. Similar to the pairwise independence concept, we call this that two random variables are uncorrelated. So if this happens, we say they're uncorrelated by definition. All right? Okay. And this is like not really important to know like what it really means in definition. But I just wrote it because you might sometimes encounter this when you're studying statistics sometimes. Because in statistics and probability, there's like a different notions of convergence. Okay, like the convergence we're used to, and there are convergences that we're not used to. And I just wanted to point this out because for two reasons. Because you're going to encounter some of this when you're studying statistics and probability. And second reason is because this notion is needed for understanding the name of the theorem, the like law of large numbers and central limit theorem. They use the concept convergent probability, but you should know at least what it means to make sure that what it means, okay? Because it's kind of different than saying just convergence, okay? So we need to know like the term convergent probability to state weak law of large numbers. So basically what it means is that we say that the random variable yn converges to y in probability if for all epsilon the probability goes to 0 as anything goes to infinity. So this means that you can kind of see that it's a bit of a weaker condition in normal convergence. What it kind of means is that because we're not thinking about the variable itself, or like probability, there could be cases where some elements might not converge, But even if that happens, those convergence will be only have zero probability. So like intuitively to understand this, it would be like, let's assume this. There's so many dots here, okay, in this space, and they all converge to something, okay, like this. In normal convergence, in order to this to hold, every element should go here, right? But what convergent probability is kind of saying, the weak condition, is that what it's saying is that maybe there will be some elements, like 1 to 3, they're not going to converge, okay? Even though other things all converge. But what this is saying is at least if you gather all these, their probability is going to be 0, okay? So that's why you're still using the term like convergent probability. Although it's a very rough intuitive understanding of the subject, so you shouldn't take it like literally, but you should like think of it like this. So basically, we're not saying every element might not converge, but if sometimes there's some like abnormalities, those things will be like very small. They will only account for very small probability, like 0. Okay. That's why basically what it's saying is that the probability that they're different, because epsilon means like they're bigger. There's going to be some gap, right? Possibly having a gap is going to go to 0. Okay? So the probability. And just for a reminder, I didn't write it in the slide, but there's also a thing called conversion distribution. You might also see them. But what that literally means is that distribution converges. So when we say like xn converges, random variable converges to x in some distribution, what that kind of means is that basically, remember that y has xn has a distribution, right? We had an fn, and just f is going to have a distribution f, right? So what conversion distribution means, this distribution is going to converge to f, okay? That's when we say it has a distribution convergence, okay? Conversion distribution, right? Which sometimes you might also see this term, so I'm just introducing you to know about this, okay? In case you don't know. We're almost done with the session. And I'm not gonna explicitly define or prove the weak law of large number or central limit theorem. 2 reasons. It's very unnecessary. You just need to know the theorem, I think. And secondly, even I don't know how to prove this. It's a very hard proof. If you want to know how to prove this, it takes really long time. Like you have to take like a graduate level measure-based probability theory in order to understand how this really works. Even though you can kind of solve this, but still. So I'm not going to prove this, even I don't know the proof. So I'm just going to state what it means, okay? So we have a weak law of large numbers. What does that mean? So basically, we're thinking of xi's, which are all random variables. There are going to be IID with the expectation finite. Okay, let me explain what IID means in case you guys don't know about this. Firstly, we can see that we have expectation to be finite because we want the expectation to be well defined. Okay? So we're making sure we're making it finite so that there's not a case where it's infinite. We don't want that case. But what is IID? Does anyone know what IID stand for? IID 혹시 뭐로 스탠다는지 아시나요? 뭐의 줄임말이에요? IID. 맞아. 사실 인디펜던트이 뭔지 아이덴티티 뭔지 잘 모르겠는데 그냥 뭐 인디펜던트를 합시다. It's taught independently and identically distributed. When you see IID, it means this. So this marker's running out of. So it means independently and identically distributed. So we already know what independent means. Literally means what we just learned, right? When we say like xi's, random variables are independent, they're like really independent. Like you remember what we did with the definition of independent with random variables? It means exactly that. But the identically distributed means this thing. So basically what it means is that even though x1, x2 and all, they are different random variables, what they're saying is that at least their distributions are going to be same, okay? So they are from the same distribution. So you can kind of see that a lot of the economic data, they're going to be like data are in this IID cases. Because when we do, like, ideally, when we're doing like surveys or when we're doing like data samples, right? What we would do is that we'll randomly select a sample, right? Making it independent. So just selecting some sample from another, it's not going to affect each other, right? Because it's like a random process. So that makes it the data independent. And we can kind of think that the data is, the sample is identically distributed. For example, if you're talking about, maybe we want to, we have a sample about people and their information about wages, okay? In that case, if we select the sample randomly, we can assume that these samples are going to be independent to each other, right? And also, they're identically distributed because they are all coming from some sort of wage distribution, right? Because a person's wage distribution is going to be not different from other person's wage distribution, right? Because they're just coming from the same wage distribution of a country, for example. So we can assume that data are going to be identically distributed. So a lot of the economic data, when we're trying to use it, we kind of assume it's going to be IID, or at least like IID up to a point. Like, for example, just for a tip, you might say, let's go with the wages still. So let's say like we have Korea data about people's wage. Okay, so we have the random process, and we can say it's going to be IID because we plug them randomly from the whole data, so we can kind of assume that they're not related, and we can kind of say identically distributed because people's wages are going to come from the same wage, right? Like population wage. And even if like sometimes there are cases where independent cut doesn't work. For example, you can kind of think that maybe like because a person's wage may be like related to other persons if they're in the same region. Like people living in Seoul, maybe like their wages are going to be related to each other in some way. We don't know. So in that case, what you can kind of do is that even if you condition the region, you can kind of say that at least inside the region, they're going to be independent. Okay. So for example, like Seoul people's wages are going to be different, structurally different from the Busan people's wage, right? But if you just think about the region itself, inside the region it's going to be independent, right? Because it's not affecting anyone, right? So at least in these cases, you can kind of say it's independent, which you'll later see when you're doing your analysis in economics. You're going to have terms like IID, or at least you have something where you have to cluster some data in order to do regressions later on when you're using the data. Those are the reason why we're kind of doing it. We're kind of making sure that data is IID form, okay? 아니, 여러분 이제 회계식 같은 거 돌릴 때 보면 이제 그런 거 많이 나오고 이런 논문 같은 데서 보면 이제 뭐에 대해서 클러스터링을 했다. 뭐 이제 현공화는 모르겠어요. 뭐 이제 리전에 대해서 클러스터링을 했다. 아니 시군구에 대해서 클러스터링을 했다. 뭐 데이터에 대해서 이런 말이 나올 텐데 그런 게 사실 그런 얘기예요. 결국에는 그 클러스팅 안 했을 때는 약간 생각해 볼 수 있는 게 지역마다 어떤 웨이지들이 다를 수 있고 이 어떤 지역적인 특성이 있으니까 서로 인디펜던트 아니 할 수 있으니까 그걸 클러스터링을 해서 마치 이제 그 클러스터링 안에서는 이제 마치 얘들이 인디펜던트 하다는 느낌을 가정을 하는 건데 그런 것도 결국 IID 같은 가정을 만들기 위한 일종의 조건을 하는 거죠. Right? So we have IID and we have the x1 to xn, we added them up. And we assume that the EX1 is going to be mu, okay? Oh yeah, we're kind of assuming that the mu are also the same, okay? For all x's. I just wrote that. Then, interestingly, there's some divided by their numbers is going to go to mu in probability, okay? Very interesting one, and you should know this already because, like, interestingly, what it kind of means is that basically, if we are having an IID data, random variables, and then you know their mean, if you sum them up and divide it by their number, they're going to go to the mean, okay, in probability, which is very intuitive. So basically, if you have small set of number, it might be not working, but if you as soon as you get very large number of data, your data is going to converge to mu, okay? So that's why we kind of use this as a law of large numbers, okay? And CLT is a different concept, but it's also very used often. So basically, I told you that, remember like telling you that, guys, that the world's not normal in a way that world's data is not normally distributed. But the good thing we can say about the normal distribution data is that even though the world's data is not normal, we can make it to be normal. So what does that mean is that we can, and that is given in central limit theorem. Basically what it's saying is that even if the world's data is not normal, if we can sample out their sample averages, what it is that their distribution of the sample average is going to have a formal normal distribution. Okay, that's what basically CLT is telling you, and which is written here. So we have a similar cases where xi's are all going to be IID, and we have said EXI is going to be mu, and we have the variance, which is not finite, not infinite. Okay, the sigma square, and the Sn is again we just add up all the random variables, and we have very similar notation except. So what it kind of means is that basically, it should be like this. Yeah. So what it means is that basically, in this sort of situation, if you have this value, you can see that this converges to chi, and what chi is a standard normal distribution. So okay. So what we can say is that basically, even if you have like a distribution that is not random variable, and you have nothing about the distribution, right? You don't have anything about the random variables distributions. We just know their mu's, their expectations, and their variances. What we can tell is that whenever, even though we don't know the distribution, if we add them up with the Sn and we set up the values, then we can make the values to go to the standard normal distribution. It's very interesting because even if you have a very, like, for example, like if you have a distribution that's for like not normal, maybe like some weird data, right? Like it goes up, or maybe this is just not normal data, even if the distributions are like that, if we get the sample averages of them and we just plot them like a simulation, what you can see is the data is going to have a normal distribution as the n goes infinity, okay? So basically, what this is telling us is that world's data, like world's population or world data is not normal, but we can make the distribution of the sample averages to be normal, okay? And that is also used a lot, so you should just at least know what it kind of means, basically. You don't need to know like overall like how to prove this. You just need to know like why we are using the term like central limit theorem, and why is normal distribution important is that we can make data into the distribution of the normal distribution, okay?